computer. All right, so this is Xiaolong. Xiaolong's postdoc at Space Telescope. Um, uh, does a variety of kind of data sciencey things. His main project is working on the so-called light echoes, and it's a real neat sort of phenomenon, and it's really exciting for Rubin in particular. And so yeah, so Xiaolong, I think you can take it away. Yeah. Okay, let's get started. Just make sure to speak up because I think the demo's okay, but just yeah. So thanks, Mike, for the introduction. And I'm Xiaolong, LSST and Discovery Alliance Catalyst Fellow at Johns Hopkins. And I'm excited to share some of my research and a quick introduction to my research topics, and later we can move on to the notebooks to do some interesting exercises. So the phenomenon that I'm currently focused on is called light echoes. The light echoes are the reflections of the transient event of the interstellar dust. And in this plot, imagine that the transient event and the Earth are on the two foci of the ellipsoid, and the light travels from the same ellipsoid, reflected the transient, and will arrive at the Earth the same time. And what we observe on the sky is the circle pattern. And as time move on, the ellipsoid expand, and we observe the rays moving outward toward the outward transient source. And if there are multiple dust shades that reflect the transient light, we can observe multiple rays at the same time, like the right animations of the light echoes from the supernova 1987A. What makes light echoes remarkable is that it gives us a second opportunity to study the historical transient that was the transients such as the Tycho supernova, which exploded 400 years ago and before the modern development of modern telescopes. But now with the light reflected by the interstellar dust, we can observe the light curves and the spectra from the Tycho supernova 400 years later after the explosions. And by the right spectra is the comparing the spectra of the light echoes from Tycho with supernova, and we can identify the Tycho supernova as a type 1A supernova. And another target that we are currently focused on is the Eta Carinae. Eta Carinae is perhaps the most massive star system in our Milky Way galaxies. And it underwent an event called the Great Eruptions about the 19th centuries. And there are only some historical record of visual brightness, estimated visual brightness recorded by astronomer John and some others. And from the historical record, we can observe that there seems 3 peaks from the great eruptions, and it lasts about 20 years. And now, with the light echoes, we can observe the light from the great eruptions again using modern telescopes. The left, the top left is the It Carina, the nebula created by the great eruptions, and the bottom is shows the animations of the moving of the light echoes, and by focus on a fixed point, keep track of the flux change, and we can recover the light curves of the great eruptions, which is really amazing. And we have about more than 10 years of observations, and by combining those observations, we recovered full light curves of the great eruption. And we can observe that from the recovered light curves, there are three peaks which match pretty well with the historical record, and they're perhaps even the first peak from our light curves, and we are investigating. And if we keep track of the light echoes, we can, it reveals the dust structures surrounding transient, which is otherwise invisible. Yes, and in the Rubin areas, Rubin will do a complete systematic survey of the southern skies, which is the first time we can keep track of all the light echoes from the historical events, such as
Can you go back to slide 8, please?
Yeah.
Okay, thank you.
Yeah, this is the middle is the variable stars, and
Is this a simulation or are these the actual?
and this is real observation from the Hubble telescope. Yeah.
What's the date on that?
The date, I didn't remember.
That's okay. Thank you. You can proceed.
This
Thank
is
you.
a very
You
famous.
answered my question. I appreciate that.
Yeah. Yeah, so LSST, we have the opportunity to keep track of all the echoes from the historical transients, such as the Crab Nebula, Eta Carina, Kepler. Yeah, and we may even discover new historical transients. Okay, and because the data volume in the Rubin areas is so huge that our group at Hopkins and the Space Telescope are developing the AI detection models to detect light echoes, and we are working on light curve modeling and the spectral identifications for in preparation for the upcoming data from the Rubin LSST. And this brings us to our exercises today. There are multiple exercises. The first exercises, we try to build a AI-based model to detect light echoes. And the model we were using is one of the models is the VGG16, which is a convolutional neural networks, and it can classify the images, whether there is light echoes, like the label as 0 here, that it's a light echo in the image, and whether we try to use VGG to classify cutout images, and we can also use some feature visualization techniques to try to understand how the VGG works. And another model we are using is called the region-based FasterRCNN. It's a more completed model. It can give not only the labels but also the exact bounding boxes of the object in the image. This is pretty useful for large images such as the survey image from the Rubin LSST. The model we will use is a famous object detection model called the FasterRCNN. The FasterRCNN has three part. The first part is like the VGG model. It's use the convolutional layers to do the feature extractions, and after the feature extractions, there's a object detection models that predict whether there is a object to propose some regions that contains the object. And the other next part, the third part is the classification model, which can do the classify and do the bounding boxes better than the previous model. And the FasterRCNN by optimize the models using the four laws the two laws from the region proposal networks, the middle part, and the two laws from the classifier part. And in the second exercises, we try to model the evolution of light echoes. In this image, that the left image is the observation from the infrared telescope, the Spincher telescope, observations of the dust near the East Carina regions, and the right image that is the optical observations of the light echoes from the dark energy camera. And when you compare those two images, you can see that the dust image and the light echo image match pretty well. This gives us points that we can, if we have the dust information, we can generate the light echo images. That's our basic idea, and we will do this by we first load the supernova light curves, and we will use we assume that the brightness of the light echoes is proportional to the dust density, and we calculate the time delays based on the dust distance from the source, and by combining the dust image and the time delays, we can create the light echo images. And yeah, and then this end of this notebook, we should be able to have animations of the light echoes like the ones we see before for the supernova 1987A. Yeah, this is the evolution of light echoes. Okay, I think this my presentations, and are there any questions? Yes.
4 slides back shows the infrared, that one.
That one, yeah. The right one is the difference image. So you can see the dark part and the white part. The dark part is the previous light echoes. The light echo moving from the dark part to the current, the white.
Where's the Carina in that image?
Corona should be top top.
Can you
top
point to
left.
it with your arrow, with your mouse?
It should be somewhere.
Oh, it's out of frame.
Yeah.
Oh,
It's like yeah, it Corona is the top. This is part of the dust out of the echoes. The it Corona is for top left.
okay. Thank
Yeah.
you. Yeah.
Any question online? Okay. And let's move to the notebooks. And the notebook is on the ZTF Summer School GitHub. It's day 4. And there are 3 notebooks, and the first notebook is build a simple convolutional neural network to for the detection, for the classifier, the light echo images and the star images. And the data set is the cutouts from much bigger images. Some imagery contains the light echoes and some have the stars, and the model is trying to classify those images. And that's the VG16 architecture and training field epochs. That's the loss function, and then we make of this we try to make predictions on the test data set. And for those who have familiar with the convolutional neural networks, can move to the next notebook for a much complicated architecture. This is the FasterRCNN. We will load the model from the PyTorch. Yeah, we will first explore the model architecture and train the model. To train the FasterRCNN, we will need both the labels and the bounding boxes, which is just coordinate four coordinates. That's our data set used to train a Forster RCNN. It includes both the class labels and the bounding boxes for each object. And same as the VGG model, we train a few epochs. We got the loss function. and make predictions. And for the third notebooks, we model the evolution of light echoes from the dust images. And first we have a simple supernova light curve. And this is the model we built from the light curves data. And next we load the dust image. This is the part of the dust image from the Spinner telescope. We will use this as our indications for the how bright is the reflected echoes. And next we can calculate the time delays, and we make a simple assumptions that the time delay is related to the distance on the 2D images. This is simplified version, so it's not 3D in real case. The center is our location for the transient event, and the color plot shows the time delays. When we combine the time delays and the dust images, we got this echo images.
I think that's cool.
Yeah, and it's and the top one is just the echo image without background. If we consider background, we can adjust the brightness of the echoes relative to the background. Yes, and then we can try to make an animation for all time phase. And there are a couple follow-up questions. Yeah, I try to answer. And if we keep track of the change of flux from at a fixed location of our animations, we should be able to recover the light curves from the event. And yeah, the next step when we combine our animation with the Rubin cadence, we will be able to make predictions for the observations of echoes from the Rubin data. Yeah. And yeah, for the second notebook, there is a large dust file. I created a Google Drive, shared a Google Drive files. The link is included in the notebook. First, download this dust image and put and put the dust image under this directory. Yeah, I think that's our exercises today. I hope you guys enjoy the exercises. I will be around if you have questions. Just ask me. Yeah.
So I don't have time points.
Aim for, yeah, well, it comes back, yeah, if Pizzo starts arriving noon-ish, we normally budget till 12:30 is kind of but probably 12.
Okay.
Yeah.
So in that case, I think then, yeah, so presentation, start, lunch, finish. Okay. Okay. Hello, everybody. I'm Daniel Warshofsky. I'm a third year, going to be fourth year PhD student working with Michael here at the University of Minnesota. And I'm going to talk to you about the project I work on called Scope, associated with ZTF. And it's all about classifying large amounts of data using ZTF, but of course will be applicable in the future with Rubin. So just kind of bones of the session here. I'm going to do a presentation for probably 30 minutes to an hour, depending on how much I blab today and how many questions people have. Then we'll start on a notebook I have prepared. And then we'll work on getting it downloaded and package dependency stuff on the first half. Then we'll break for lunch, and then afterwards we'll work through the notebook. I'm hoping it should be pretty self-explanatory, but if not, I'll be here to fix any issues and maybe make do some live coding bug fixes for you all, but hopefully not. So yes, that's the structure of things. Okay, and I do have my Zoom open, so if there are Zoom questions, please feel free to let me know. Okay, so start off. Everybody knows what this is. This is the night sky. There's lots of stars all over, and when you look up every night, things generally look the same. But I think we all know that the sky isn't really static. There are lots of different motions. Like, for example, you have just daily motions from the sky, and seasonal variations, which cause the sky to change, or retrograde motion of planets also cause variation in the night sky. But this really isn't the kind of variation. This really isn't the kind of variation we're interested in. This is kind of very, this is groundbreaking maybe 1,000 years ago. Not so much for us. The kinds of variation we're interested in are transient sources or variable sources. So just as like a quick overview of just some transient sources, you have things like supernovae, which are the very explosive end of life of massive stars. Tidal disruption events, which are stars getting basically ripped apart by black holes, and neutron star mergers, which cause ripples in space-time that we can detect with LIGO and whatnot. And this is just like a handful of various transient phenomena that are out there. And the key about being transient is that they appear and then in a human amount of time disappear. And this is not the focus of what I'm going to be talking about, so I just have the slide here. What I'm more interested in are things that are variable. So these, as opposed to transients, variables, they also change brightness like transients do, but instead of disappearing forever, these things are persistent sources through the sky. So while you have to be sort of lucky to catch a transient, these variables are out there hiding in the data, just doing their thing. So I'm just going to go over a couple of different kinds of variables and divide them into a couple categories that will be will be more meaningful later. So to start off, here's a class that I call accretors. These are variations that are powered by material falling into a big gravitational potential. So, for example, you have like AGN. So matter is falling into a supermassive black hole. There's a deep potential, so there's lots of energy, and different AGN have been classified as different things, but this is due to a viewing angle. And on the right is just the sort of the unification model of all the different kinds of AGN and how they were classified based on their viewing angle. So this has variation associated with it as different pieces of as the accretion rate changes, the brightness changes as well. And but they're persistent sources. They're kind of here for a while. Another kind is a CV or cataclysmic variable. This is when you have a binary system with a white dwarf, and the white dwarf starts to rip the material off of its companion star. And as this is falling in, variation in accretion rate or buildups on the surface can cause flares, and this is this is another source of variation out there. Also, so another class, we have binaries. One of the main kinds of variation you see in binaries is due to eclipses. So here's just this schematic of a binary system, and you can see you get this time varying light curve only when you have an eclipse happening and the system is edge on. Otherwise, you can fully see both of the stars. Again, this is a very basic case. I just kind of want to go over a bunch of things before getting to the main point. And last, I want to talk about our pulsators. So these are stars that kind of puff up, and when they puff up, their puffing causes there to be variation. And just to kind of schematically go over how a lot of these are driven, they're driven by a process called the kappa mechanism. So what happens is in an outer region of the star, there's a layer where the conditions are just right for ionization to be favorable. So when this ionization happens, in this like orange layer here, you get a bunch of free electrons, and these free electrons increase the opacity of the layer. So with the increased opacity, you get increased radiation pressure coming from the interior of the star, and that causes it to be pushed out and expand. As the star expands, its radius gets larger, so there's a bigger surface area for light to be emitted. So this causes an increased luminosity of the star. But as it expands, the temperature and pressure are changing. So recombination becomes favorable again. These free electrons get they're no longer free. And then gravity starts to win again and the star contracts. So you get a cycle here where you get ionization and expansion, then recombination and contraction, and you go through a cycle like this. Now this is what's driving this expansion. The period of this expansion is mostly caused by the characteristic frequency of the star, which is mostly determined by its size and composition. So some famous pulsators are the Cepheids, which have been used in the past and current to calibrate the distance ladder. So these are really important variable sources in the universe. Okay, so we can skip the slide about ZTF. We all know what ZTF is. But the key thing about ZTF that's important for this and in terms of Rubin in the future is that even just with ZTF, there are over 4 billion light curves. And all these interesting, at least I think, interesting variables are hiding inside of the data, and it's hard to get them out. So like this is the key point, is that there are too many variables to do things by hand manually. So in the past, people may have found lists of thousands, maybe 10,000, and that's a reasonable amount of sources to go through by hand and try and find variation. But it's just not feasible when the data is this large. And with Rubin, it's going to be even worse. So we need to automate the procedure, and I think everyone can predict the next slide is going to be machine learning. This is a great way to automate this kind of classification procedure. It's been done in the past, but you've heard about machine learning a lot, but this is sort of my perspective on it. So people think of machine learning as something that's really new and up and coming, but actually it's quite old. I think one of the first days we talked about the perceptron, but it goes back all the way to the 40s that machine learning was thought of. But what's really brought it into the forefront now is the cost of GPUs and GPU compute. And for astronomy specifically, the industry's interest in doing machine learning on images has been really useful for astronomy, because we can sort of borrow things commercially designed for images and use them on images, which is what most of astronomy is. And the key for me, at least, how I sleep at night with machine learning is I think of it as fancy statistics. This is how I justify it for myself. It really is, you're just fitting a really complicated model, and there are no boogeymen inside the algorithms. Okay, so let's go to my specific project. So this is the scope, the ZTF source classification project. And the idea is to take all of the data in ZTF, all 4 billion plus light curves, and try and classify them based on their light curve and determine their variable properties. And this is sort of schematically how the process works. So we're taking in the light curves and external data. We're computing some features, which I'll get into. The features then spit out classifications, and then through a process called active learning, where basically you get a bunch of experts to manually label data and correct the classifications. We go through this loop to train this large model. And then finally, when everything's done and we've decided the models are good, we ship the data off to the public, which is, the cloud here. So something that I think there's not enough focus on when doing these large catalogs. A lot of people focus on this aspect here. So the classification, the trained models, the inference, active learning, but actually a lot of computation goes into making features, and it's I think it's a lot of times overlooked when you're looking at performance of machine learning algorithms. So I want to kind of take the time to get you acquainted with the features that we use for scope. So here's a list of a bunch of features. They're into 3 basic categories. First, I'll call basic statistics. So here's just a big list of what I call basic statistics. These are things like the median, skew, there's like a chi-squared, interquartile ranges. These are things that are pretty cheap, easy to compute, and have been used in historic studies of variables. The next slew are auxiliary information. So these are things from external catalogs like Gaia, WISE, and Pan-STARRS, as well as things like the number of alerts generated from ZTF. This also is pretty easy, but then we get to the hard part, which is, that's this one. Then we get to the hard part here, which is computing the period. The period is very difficult to compute, and I'll go over how we do that in a little bit. But it's also really important in determining what kind of variable object something is. So some things have short periods, some things have long periods, and that's a really powerful way to determine what something is. So CVs have shorter periods, whereas long period variables, given their name, have long periods. So determining the period is really good, as well with the significance. If there's a low significance in the period, then it's likely non-periodic. So that's an important thing in the classification. Unfortunately, it's one of the most expensive things. And then there's also this wacky feature here called the DMDT histogram, which if you want to know more about, you can ask me, but I'm just gonna skip over it. It's used in one of our architectures. Yeah. So okay, computing the period. So this is what a light curve looks like. So some key things to notice here, really important, is this axis here, which is the time period. And you see this goes over 2,000 days. So this is a lot. So this is a lot of data. And when you look at it, it looks like there's some variation, but by eye you can't really tell if it's periodic or not. So how do you go about determining if something is periodic? Has anyone done period analysis before? Does anyone? No? Okay, great. So I'll go into lots of detail here. Okay.
Is that points in between, like, because the telescope was not pointed at that?
Yes. Yeah. So another thing to say, that's a good point. So another reason why you want to compute features is because not every light curve is going to be sampled exactly the same way. Some have more points, some have less, some have gaps, some don't. So it's difficult to find a scheme that you can really dump the raw light curve into. And there are ways to do interpolations, like using a Gaussian process, for example, but that's just, and for me, this isn't really worth it because we're doing some computing to fit our data into the machine learning algorithm. Is just doing this interpolation, where instead we could do this feature calculation that you can then use the features calculated in other sort of historic style studies, where knowing the period or knowing the mean and the amplitude, these things can be used in other kinds of searches that aren't machine learning. So you get a little bonus, in my opinion, when you're computing the features, and it lets you condense every light curve and evaluate them on equal footing, basically. So when you want to find the period, believe it or not, it's as simple as guessing. So if you guess what the period is, you fold it on the phase. So basically you're just taking the time axis and doing a modulo operation on the period. And then you look at it and you decide, you look at this and you say, is this periodic? Or more sophisticated, you evaluate some statistic on it and determine if it's periodic. And I'll ask you guys, does this look periodic at this guess?
No.
Correct. This does not look periodic. So we try again, and oh, look at this. We get something that's a little better, and yes, this is periodic. But it's not as simple as this, because when you do this guessing and checking, some things are obviously look good, some things obviously look bad, but there may be multiple periods that look good or bad. For example, if you look at a period that's twice what I have here, it's also going to look periodic and would score high in a statistic, because just think of like if you track the brightness of the sky, you would see every 2 days it looks like about the same brightness, but we know that the true period is only 1 day. So you have to come up with some way of determining what's good or not. So here's something called a periodogram. So on the x-axis, you have basically all of the guesses, and then the y-axis is telling you how well that period was. And you can see there are these peaks here, And the true period is the highest peak here, but it's not always as obvious. Yeah, Tyler.
What would the effect be if you essentially just like dumbed it down and just looked for like the shortest period that was above a certain number of standard deviations, not consolidate?
Well, I would say,
Like you just stop there with evaluating higher periods.
well, the true answer is this is done on a GPU, so all these are computed at the same time. If if you're doing this on a CPU, then maybe you could do that. But you get into problems with when you're looking at the harmonics and how you would compute the grid. So for example, if you decide to early stop at this one here, because there's some distance here, then you wouldn't actually find the true period. So yeah, so you get a bunch of these top peaks, and you need some algorithm to decide which one is good. So, like I was saying here, so these things here are likely harmonics of the best peak here. So basically integer or mixed number multiples of the true period, and then you get all sorts of other weird effects here. Like you get this secondary peak here. There is some, other periodic thing going on. So it's, even if you're doing this guess and check, it's still non-trivial to figure out what the best one to use is. The y-axis is the statistic. So, this one, think of this more in abstract. That's about a specific algorithm or not, which I'll talk about a little bit on the next slide. But basically the idea is, this is to illustrate that even if you do this guess and check, it's still non-trivial to decide which one is the best. So there's different ways to do that. So, and different period finding algorithms have different bias. So to kind of avoid part of this problem, we use 3 different period finding algorithms at the same time, which adds to the computation cost. So we use 3 of them. So Lom-Scargill and conditional entropy and analysis of variance. And these basically fit into two subcategories. The Lom-Scargill, I view it, there's lots of ways to interpret it. The way that is most useful here is it's basically doing regression. It's basically doing model fitting for a sine wave. But to your question, the Lom-Scargill, you can, in its best, most pure case, is equivalent. If you get perfect data and just under the right assumptions, the Lom-Scargill is very close to, if not equivalent to, doing just a Fourier transform, which is sometimes also called the classic periodogram. But the key is it's looking for sine wave things. And there are things that vary and are periodic that don't that aren't sinusoidal. Like a classic example is an Ara Lyra. They have more of a sawtooth shaped light curve where they rise rapidly and then fade over slower times. So a Lom-Scargill may not be as good at picking that up. But Lom-Scargill is very good at picking up sinusoidal things like transiting systems, for example. The other 2 algorithms, conditional entropy and analysis of variance, are I think they're like histogram dispersion minimization type things. So you basically fold your light curve and you plot it, and then your kind of goal is to minimize the vertical spread in each bin. So these are agnostic to the shape of the variation. So these help find the sort of non-sinusoidally varying things. And then how we tackle this like peak problem is, so we compute for all of these, and then what we do is we take the best 50 scores from Lom-Scargill, the best 50 scores from conditional entropy, and we take those test periods, and then we rank them against how well they perform in analysis of variance. So we're kind of doing like we're kind of doing using analysis of variance as a tiebreaker to hopefully kind of break some of the degeneracy between things. So this is how the period is being determined, which is, spoiler, one of the most important features. Okay, so now we've talked about the features. Now let's talk about kind of the specifics of the algorithm. So unlike a lot of other machine learning projects that I've come across, scope splits scope is not one machine learning classifier. It's a whole family of them. And yeah, hold on, I'm going to explain this back. Okay, there are two sets of classifications for scope. First, you have the ontological classifications, which are based on kind of the scientific names of things. So if you look here, for example, here's this pulsator category I brought up before. And if you look through here, these maybe are some names you recognize, like an R Lyra or a Cepheid. So these are classifications based on kind of I think I had to zoom in of it. Yeah, I did. Based on the kind of the name, what an astronomer may have classified something in the past. There's another set of classifications called the phenomenological classifications, and these are a little more abstract. So if I zoom in on this section here, so you may want to know if something is periodic or not periodic. And then you ask a question, how is it periodic? What does the light curve look like? Well, maybe it has eclipsing features, or maybe it's sinusoidal, or sawtooth, like I was saying before. So this is a more abstract, yeah.
Wrong period.
Wrong period means it's periodic, but the period that came out of the algorithm is incorrect. So some really common wrong periods are guessing half the period or twice the period. And you can get a lot of wrong periods when doing eclipsing systems. So for example, imagine you have a system where two objects that are roughly the same size and temperature, each transit is going to look approximately the same, but the true period is going to be when you get two transits, because A in front of B, then B in front of A, but it's likely only going to pick up on half the period. And same thing with double. These ones aren't very good though. So yeah, so these are the classifications, but back to like a big one here. A lot of machine learning algorithms will take all of these classifications and slap them together in one giant vector. This is not what's happening here. Each node you've been seeing constitutes two different independently trained machine learning algorithms that tell you is something that class or not. So it's sort of a one versus other classifications. And they're all trained independently of each other. There's no normalization that happens amongst these scores. A lot of the times you get a vector at the end where the sum of all the numbers is one. This is not happening here. So you might think, oh no, we've lost this really nice probabilistic interpretation of the results. And you're right, we did lose that really nice probabilistic interpretation of the result. But what we gain is this like subset hierarchical structure where we can have non-mutually exclusive classifications. So if we put all these together, it wouldn't make sense to have variable and flaring, because those would clash against each other. But here we can, so we could do wider searches and say, I want to know what all the variable sources in this little part of the sky are. And then maybe later I want to look at the flaring subset. So this gives a lot more flexibility in the classification scheme. Also, another thing that helps is, say we discover a new kind of flaring irregular object. In principle, we could just train a new node and slap it right here, and we don't have to touch anything else. So this allows us to add new classes without having to retrain everything, which in a more standard kind of model, you you would have to put everything in and do some retraining. Now you can get away with a lot with more recent advances in pre-training models, but since it adds a lot of flexibility there. But we do lose the really nice probabilistic interpretation. Yeah, this is kind of one of the big cruxes of how this is different from other classification things. So if there are questions about this, please ask now. Yeah.
Can you go back 2 slides? Yeah, right here, and then the next one. Thanks.
Okay, any questions about the classification scheme and how this is all structured? This is non-trivial in my opinion, and I work on it every day.
When you put your final classification on the cloud, like how do you report it? The classification?
So I give there's a couple columns of like metadata, like where in the sky it's located, a couple IDs and cross-match stuff. And then for each node, there is a score reported from 0 to 1. But the sum of those may be 88, which is like the total number of these. Also, one thing I forgot to mention, each one of these is two classifiers. There's a deep neural network and also an XGBoost tree algorithm there. So there's some redundancy as well in that. So every node gives you 2 numbers for every single source in the northern sky with ZTF. So it's a lot of numbers. There are a lot of different classifications. Okay, yeah, so there's, like I said, there's a deep neural network. Here's my interpretation, how I like to talk about it. So you have your features on the left. All these nodes are connected by basically a linear transformation. But then when you get to the nodes, you do the fun nonlinear stuff, which makes machine learning actually accomplish meaningful tasks. And then at the end, you get a score reported from 0 to 1. So every node that you saw in the tree is reporting a score like this. So you're doing one of these for all of the different sets of classifications. Yep, linear transformation. Okay, and here's like the under the hood type thing. So inputs, there's kind of 2 trees here. This is dealing with the DMDT stuff, which I didn't really talk about, but it's a 2D histogram, so it gets to use all the fun convolutional the 2D image convolution stuff. Hooray, fun. Yeah, so you have the densely connected regions. These are like the normal linear transformations with the activation at the end. We've got dropouts, which help, which randomly drop some of the features, which help against overfitting. And there's also these convolutional layers. This is what a convolution is. Don't worry about it. So here, the XGBoost. So, yeah, what is it? It's the like extreme gradient boosted decision tree, I think is its full name. The idea is you have some data in some abstract space, and they have classes associated with them. Here I have circles and triangles, and what the decision tree is trying to do is make a partition in the space that separates the classes. So here, triangles are on one side, circles on the other. And one tree only does so good, right? Like it didn't get these ones right, and this circle is not in the right space. So maybe one tree isn't enough. So let's try again, and we make a new tree, and it has some different kind of classification. And it does better on these guys here, and it did better on this guy, but it did worse on these triangles over here. So ideally, we'd have maybe multiple trees working together to help make things better. So like, for example, you put them together and you can make a better classification here. So we've got these triangles better and whatnot. So there's different ways to kind of aggregate multiple trees together. And the 2 common ways are bagging and boosting. So on the left, left is a sort of the schematic of bagging where you're taking, where you're training a bunch of trees pretty much independently, and then you take their results and then you aggregate the results, and that gives you your score. On the other hand, you have boosting, which is a bit more complicated. What's happening here is you train one classifier, and it does well on certain things and does poorly on others. So when you go to train your next classifier, you tell it that the first classifier did poorly on to give a higher weight to, so it does better at classifying the things the other tree didn't classify well. And you do this step over and over and over again, and then you take and then you aggregate the scores of the classifiers. And this is really good for picking up on maybe rarer classes that you're missing consistently from various trees, but it does run the risk of doing of overfitting and being more susceptible to all of these overfitting type things because of that. XGBoost does, as the name suggests, boosting, so it's doing something more along the lines of that. Okay, so the training data. So also very important for machine learning is how good the training data is. And we're very lucky to have been able to pull a bunch of experts and have a training data set of over 170,000 manually classified light curves from ZTF. And here's just basically showing how many sources, this is log scale, by the way, how many sources of each class there are. And a reminder that the sum of this is going to be more because there's this like subset relation going on. So, all of the variable sources, all of the periodic sources are also variable and stuff like that. So you can see, yes, you can see all of the stuff here. So how good is the training? So if you look at how well do the algorithms agree with each other, so you can see, so the color code is telling you how many positive examples were in the training data. So yellower is more and purpler is less. And you can see when you have a lot of sources, both algorithms, so yeah, DNN on this axis, X should be on the other. So when you have lots of sources, the algorithms tend to agree pretty well, both in the precision and recall. And when there's few, it does bad. So as expected, fewer sources does worse, more sources do better, which is good. And then just to see how things are in regards to overfitting, basically this is the difference in the scores between the training set and the testing set. So if there's no overfitting, things are more likely to suffer from issues of overfitting the further they are away from this zero line. So zero is saying the scores from the training and the test are identical, and that means that gives you some confidence that there's nothing special about the training set that was learned, and that it's more generally applicable. And the XGB classifier is suffering more from this issue, which is to be expected because of the boosting. But overall, things are pretty well. And in general, like a rule of thumb that I use when I'm combing through the data is like the sources the classifications kind of this way of this line are not really super reliable. And these are ordered in number of sources. So there's more positive examples to the left and less to the right. So this is basically to say this is all pretty much expected behavior, nothing out of the ordinary here. One great thing about tree-based algorithms is you get the importance of each feature for free. Whereas with a a neural network, you have to work a little harder to get that. So we can look and see what the important features are. Does anyone have a guess of what some of the most important features are?
Period.
The period. Brightness, yeah. So like the intrinsic brightness that something is and the period of it. And if you look here at the features, so this is, again, because we have this weird scheme, the feature importance is a little more convoluted than you normally expect. So for each time that one of these features appeared as one of the three most important features in any of the nodes, it gets a tick here. So if you look at the top, you see here light curve period value. So the period is the most important feature, or it appears to be important in tons and tons of these. Next, you have normalized chi-squared and best fitting Fourier series. This is another statement about the period, how how well, like this is a Fourier thing. So we're talking about the frequency stuff here. So this is a thing of the period. Gaia parallax. So this seems like a little odd to come in here, but this is actually telling us about the distance, which in turn is telling us about the intrinsic brightness of the source. So this is basically telling us how bright it is. And then the Gaia color is giving us like an idea of where this is on the HR diagram. So basically, to not really much surprise, the most important features are the period and basically where this thing lies on the HR diagram. So it's not super surprising there. Yeah, you can look over. There's lots of fun things to look at here. I mean, looking down, let's see, inverse von Neumann ratio. That's something in the literature. Bayesian information criteria of best fitting Fourier series. Again, something to do with the periodic nature of things.
To the deep neural network and the tree algorithms get the visual importance, how different are they?
The deep neural network, the tree-based algorithms, you get this feature importance basically for free. When you want to do a feature importance with the neural networks, or at least in the infrastructure that we use when this was created, this is not the newest construction of this. You usually have to do like a permutation importance, which is basically like retraining and testing without a feature. So that involves lots of retraining. So it's not as free as you get with the tree-based one. So this is only for the tree-based, not for the deep neural network. We don't have that for the deep neural network.
Here's how
Yeah, I'd expect it to be pretty much the same. I have no reason to believe that it would be much different. The neural networks use the DMDT histogram, which it didn't mention, but I imagine that would show up as having some high importance because it is encoding the full light curve a little bit better than any single one of these would. So I'd expect that would have a higher importance. But other than that, I have no reason to believe that these would be much different at all. Just because the scores agree so well, I have a hard time believing it before. Okay. So next. So this is like the current status of the project. So it's still in progress because computing the periods of all of these is really computationally expensive. But this is a map of the sky where the cotton candy blue region is the part of the sky that has been fully classified and features computed and is publicly available on Zenodo at this link here, which constitutes almost 700 million. So it's close to halfway. There's about 2 billion sources that meet quality cuts. So close-ish to halfway. And it is covering a large region of the sky. So yeah, that's the current status. And then the next thing is to start to go into the activity. So if there are any questions about this now, please ask.
Does this correspond to the fields that we've been studying?
Yes, so you see it's a kind of like a bit boxy. So that's because ZTF cuts the sky up into fields. And I'm just going through fields, basically RA, like 15, basically an hour at a time in RA. So I'm going on two different ways. So I'm going this way, and then I'm also going this way from this chunk. So yes.
When you do the training on the model, you consider the uncertainty in the data.
I believe that is I think that's actually, I don't think that's one of the features. There's uncertainties that come from external catalogs that are part of the features, but since each light curve point has its own error associated with it, we're not passing through all of the errors altogether. But like some overall summary statistics are included, like the standard deviation of just like all of the points in general is included. And thinking into the code that does this, I believe it does not it does not take into account the individual errors when computing those things. So the answer is no, does not include that. Though probably could have. Hindsight.
Yeah, I mean, I think it'd be really interesting for someone to try kind of the time to event type thing with, the photometry. The question is, well, there's one question, like, can you not have to period find?
Yes,
And
that's the Holy Grail.
that is the Holy Grail. But could you get away with something, like one of the principal markers or something to try to, but for now the answer is no, and I think that's a weakness.
Yeah.
Yeah.
The field has really advanced a lot since the inception of this project. I feel, at least in the neural network side of things.
Yeah, I would say.
So the neural network side of this is probably not as like architecturally impressive as you may see as like things today. So really the novel part of this is not necessarily the architecture of the machine learning algorithms, but it's more of like the organization of the classifications and sort of the scope of the project, pun intended. So that's kind of the key. Those are like the keys here. And the idea is that this is going to provide a gigantic catalog for all of these. Every single one of these, you can say, I want all of the sources that score above some number, and boom, you have a nice catalog of it. And on top of it, you can do things more, and because of the phenomenological tree, you can be more abstract as well. So if you're searching for transients, well, you don't really care if something's an R or Lyra necessarily, or care that it's a CV necessarily, but maybe you care that something's flaring and it's something in the galaxy that's flaring. I don't care about things in the galaxy are flaring, so I can search all the things that kind of meet this general criteria and just ignore them in my transient search. Or you can, there's all sorts of, there's a rich, it's a rich data set that you can use in lots of different ways for different reasons. You can do so, you can use the ontological classifications to kind of do the kind of science that has been done before, like show me all the Cepheids. I want to find them, follow them up, and see what they're all about. Or you can maybe try and do like things that are a little more odd, like I want things that are sawtooth and flaring, and look for things that meet both criteria and try and find these wacky sources. So this is the more novel and interesting part of this. And the hopes are this will also the classifications from here, the sources, there's overlap between ZTF and Rubin. So you can use the sources and classifications from here, find, cross match into Rubin and start working on training a new set of classifiers. Maybe not the same exact architecture, but maybe a similar kind of classification scheme, and do a similar thing in the southern sky, is sort of, looking towards the future, how stuff is going on here. Any other questions? Also, ZTF is looking fainter than a lot of these like larger legacy surveys. So I said, the ordinary science, right? But now you're looking at things maybe closer to 20th magnitude instead of like 18. So that's also like a huge volume increase as well. So that's another part of the project that I kind of just glossed over. Any questions? Okay, so then activity time. Okay, so the goal before lunch is, okay, so here's the activity. So we're gonna run through a notebook on this GitHub page, and if there's time in the session for later, we can try and your bonus is to search, use the catalog to search for Cepheids, and use the periods provided by the catalog to see if you can recover the relation between the period and brightness of Cepheids. So this is the activity. So first, so you guys are gonna clone this from the GitHub, and then I think it's pretty basic packages. You'll just need to pip install Kowalski, which you might have done already, I'm not sure. And then here are your credentials to access the database as well. So the first half is going to be basically cloning the repository and getting the right packages installed. And then after lunch, it should be running through the notebook, which should take the rest of the time. Also, as a note, section 6 and 7.2 of the notebook will not work because this credential does not give you access to the databases for it. You get access to the other stuff. It's pulling the individual light curves, which is not part of the project, and we couldn't restart the other server to make sure these credentials aren't permanent. So yeah, so if you like the catalog, you can contact me and we can set you up with an account. These credentials will disappear after summer school is over. Okay. So